So suppose that we have the following integral on the curve. Remember, this little circle means it's a closed curve. Starts and stops at the same point. We have 11x squared minus 4ay dx plus 6x plus 9y squared dy. We're told it's equal to 66. C is the boundary of a region on which Green's theorem holds. Now, I suspect this is probably a clue that we should be using Green's theorem. We're not going to let that clue pass us by. If the area enclosed by C is 3 square units, find the value of the constant A. All right, so let's write down Green's theorem. We have that the integral along a closed curve of m dx plus n dy is equal to the integral over the region that it's enclosing, right? Because it's a closed curve, so there's a part in the middle. That's the region it encloses. We're going to take n sub x, subtract m sub y, and dA. This depends on the orientation being correct. However, given the assumptions, we're going to assume that the orientation is correct. If the orientation were wrong, that'd be a negative sign, but that's a whole other story. Not for this problem. Now, for us, we have our m and our n. So let's take these derivatives. This is equal to the integral over our region of n sub x is 6. M sub y is, see, that goes away, negative 4a. All right. Well, that's really 6 plus 4a. Now notice that's a constant because a is a number. Constants can be pulled out. So this is 6 plus 4a and times the integral over our region dA. Well, what happens if you add up the integral of your region dA? Well, what you're doing is you're taking your region R, you're splitting into little tiny pieces. You're saying the contribution from each piece is the area of the piece. Then you're adding it all back up. It's the area of your region of R. So we're like, hey! So this is really like 6 plus 4a times the area of our region. Now, do we know what it is? Yes, it's 3, right? Because it said our region has area 3. Okay, so let's go ahead and mark that down. So I say, all right, so this 3 comes into there. So we get this as 6 plus 4a, whoops, capital A, times 3. And finally, we're like, great. And remember, it equals 66. We didn't mark it down at the start. So we can just, this equals 66. And we're basically home free, right? So divide both sides by 3. 6 plus 4a equals 22. Subtract 6 from both sides. 4a equals 16. And a equals 16 divided by 4, which is 4. And there we go. Nice! Now, one of the things you're going to notice here is on a lot of these problems, we're going to not do a lot of integration, or we're going to do very simple integration. And kind of the theme here is to say, how can you take the problem and use the tools to make things simpler? Because we like things being simple. And all right, so one problem down, right? Good. Let's keep going. Let R be the region in the plane formed by taking the triangle with vertices at 0, 0, 8, 0, and 0, 6, and then on each side attaching a semicircle. And let C be the boundary of R traversed counterclockwise. See the diagram. All right, so here we go. So here's the original triangle. We have the 0, 0s here. We have 8, 0. That's over here. We have 0, 6. That's up here. And then we've replaced the triangle, which is marked in these dotted lines. The sides have become pushed out into these half circles, these semicircles. All right, and then we have C as our boundary. We can write it down here. You'll notice it's been oriented. And we can add a few more arrows just to help us emphasize. It's oriented in a nice way, counterclockwise, the way that is consistent with our theory. All right, now we're asked to do something. We're asked to find the value of this integral, but of course, it also says we should use Green's theorem. Now, that's a subtle clue that we should use Green's theorem. And you might say, are they always going to be so blatant about it? Not always. So what are we looking for when we're looking for Green's theorem? Well, the big thing you're looking for, two kind of things, to be honest, is this kind of an integral. So you want an integral which has that little circle, which means a closed curve. That's what you want, closed curve. The other thing is you want to have sort of orientation matters. In other words, either m dx plus n dy or f dot t ds or f dot dr, one of those things. And so those are the pieces you're looking for. Closed curve, orientation matters, m dx plus n dy or f dot t ds. All right, so let's use our theory, right? Okay, so that we can start by saying, if we call this part m, call this part n, then this is equal to the integral over our region of n sub x minus m sub y. And notice we go from a one-dimensional to a two-dimensional. All right, they might say that sounds like it's become harder. Maybe. It depends on what happens with derivatives. Well, what is n sub x? Derivative of n with respect to x is 7. Okay, that's a 7. M sub y? Derivative of m with respect to y is 4. All right, 7 minus 4, 3. So we can pull the 3 out. So this is 3 integral over our region dA. We've mentioned this before. If we integrate over our region dA, what are we really finding? Well, we're really finding the area of our region. And don't forget to multiply by 3. So, okay, so we just have to figure out what's the area of our region. Now, let's think about what shapes we have involved. Well, we can think of it as there's a triangle. And, well, what do we know about this triangle? It's the right triangle. Good. I hate it when we use the wrong triangle. We always want to use the right triangle. And, all right, well, do we know theta? Yeah, we know the base. We know the height. And so we could say, okay, so we have 3, and we have 1/2 base height. Okay, there's triangle. Now, what about these circles? Well, this circle, this total length here is 6. That's the diameter, so half of it is 3. So this is a half circle, so we're going to have another factor of a half. And then we're going to have a pi r squared. So that's the circle on the left. Downstairs, well, this length here is 4, right? It's half of length 8. Again, it's half a circle, so it's 1/2 pi 4 squared. That's the bottom circle. Well, what about this length? Well, these numbers might be suspicious, right? When you see right triangles and you start seeing 3 and 4, you're like, oh, could it be a 5? And it is a 5. So you can do Pythagorean theorem. 6 squared plus 8 squared, 36 plus 64 is 100. So that means this length, the diameter, right, from vertex to vertex is 10. Half of it, which will be the radius, is 5. So you have a 1/2 pi 5 squared. All right, so there we go. Now let's see if we can't clean this up a little bit. Well, 1/2 times 8 is 4 times 6. This will make 24. And here we can go ahead and pull out a 1/2 pi. Then we'll get 9 plus 16 plus 25. And 9 plus 16 is 25, plus another 25 makes 50. times 1/2 pi, this makes 25 pi. So we end up with 3 times 24, which is 72, 3 times 25, which is 75, and don't forget that pi, and there we go. 72 plus 75 pi. Nice. So in some sense, really, Green's theorem is mostly testing on, do you understand when it can be used? Make sure you can understand this computation. And it turned into not an integral problem, but a geometry problem. And geometry is fun, right? It's thinking of shapes, how things all fit together. So, all right, be ready to do some geometry. Find the surface area of the portion of the plane 4x minus 5y plus 2z equals 7 that lies within the cylinder x squared plus y squared equals 9. All right, let's talk about what's going on. So what do we have? We have two objects, and we just want to understand how they're interacting and what it is we're actually finding here. So object number one is we have this plane in space. I'm not going to stress too much about getting it just right. I just want to understand the intuition right now. So here's some sort of plane out in space. And then we have the cylinder. Now, notice it doesn't feel like a three-dimensional object because it has only x and y. It feels like a circle in the plane. But when there's no z, you take that circle in the plane and you copy it up and down. And that's how you end up with the cylinder. So you say, okay, so then we have this cylinder, and it's moving up and down. All right. Now what's going to happen? Well, somewhere this cylinder is going to intersect with the plane. And where it intersects, that's what we're after. So the question is, okay, what's that area? That area right there. The part of the plane in the surface. So imagine you're taking the cylinder, and it's like a stamp. You're stamping out a piece of the plane. You say, okay, well, how would we figure that out? Well, let's think about what's going on. We can set this in three-dimensional space. In fact, turns out that we have that the cylinder goes straight down the z-axis. And we say, well, if you look at it, it's lying right above the circle x squared plus y squared less than or equal to 9. So that's this part down in the plane. So what do we have? We have sort of a plan. Now, using our surface integral notation, if we think of this surface here as g, what we're really trying to find is the integral of g dsa. Right? Because it says, take your surface, break it up into little pieces, and for each piece, you're just saying, what's the size of that piece, and add it up. So that's the area. Okay, now what we're going to do is instead of trying to do it in the surface, we're going to push it down into the plane. So we're pushing it down into an xy setting. So, okay, so this is going to be equal to the integral over our region R. So here's our R, this is R downstairs, we'll get back to that in a second, of the dsa. Now, there's no other piece that we have to convert. Maybe we'll do that on a different problem, but not this one. Okay, so what is dsa? So that's the square root of 1 plus f sub x quantity squared plus f sub y quantity squared dA. All right, so this is the computation that we have to run. And when it comes to surface area computations, we run into this formula, and in just a very small number of cases, we are like, okay, we can work with it. We are in one of those cases. So let's see what's going to happen here. So here we go. Let's try this out. Now, first off, what's f? So we're going to take our surface, 4x minus 5y plus 2z equals 7, solve for z. Because when we talk about this surface, we're going to think about this as being z equals f of xy. So we need to solve for z to take these partial derivatives. So we're going to move things across, get 2z equals minus 4x plus 5y plus 7, divide by 2, minus 2x, 5 halves y, 7 halves. All right, so this is our f of x, y. Now the good news is these are nice functions. They're flat functions. We love flat functions. Let's take our derivatives. What is f sub x? Well, there's only one x. So f sub x is going to be negative 2. What is f sub y? There's only one y. So f sub y, that coefficient, 5 over 2. So this becomes the integral over our region, square root of 1 plus negative 2 squared, which we can write as 4, plus 5 halves squared. Well, we can write that as 25 fourths, and dA. Okay, well, we're pretty much home free now, because there's a couple things to note. First off, let's clean this up. 1 plus 4 is 5. We can write that as 20 over 4. So then we have a common denominator, which is really, this is 45 over 4. Now, we can take the square root of that, and if we did that, what would we have? Well, the square root of 4 becomes a 2. 45 is 9 times 5, so that would leave us with the 3 square root of 5, right? Square root of 9 is 3, and square root of 5 is square root of 5. Now, the other thing is to say, hey, whoa, hold on a second. That's a number. Yeah, it is a number. We could pull it out. We could pull it out. So we're going to pull it out. So we say, okay, pull it out. So we get 3 square root of 5 over 2 times the integral over our region, dA. And at this point, you're like, broken record. Steve is just going to say this is the area of our region, because it is. So now we're like, okay, so what is our region? Well, it's what's in the cylinder, right? Because we have this flat thing at an angle, but when we push it down, what you're really doing is you're coming up to the top of the z-axis, and imagine that you're looking straight down the z-axis. As you look straight down the z-axis, what do you see? You're seeing something in the xy plane, and what you're seeing is what would be, you might call it the projection down onto the xy plane. And in this case, because you're taking just what's in the cylinder, you're seeing that circle. So, what's the area? Well, it's the area of a circle of radius 3. So, this is going to become 3 square root of 5 over 2 times pi 3 squared. So we can write this as 27, 3 times 9, square root of 5 times pi over 2. And there we go. So it turns out that for flat things, which includes planes, we can do pretty well at surface area. It's when things aren't flat that the inside becomes messy. But, well, maybe we'll have a chance. Maybe. But all right, we did good on this one, right? Let's keep that going. Let f be a vector value function. Now we know it's vector valued. They're giving us a hint by writing it with the bold f. So it's a function times I, a function times j. Let c be the path along the x-axis. Oh, we probably should draw this. So let's draw this. So we're going along the x-axis. We're starting here at negative 2. We're moving to positive 2. And then along the semicircle, y equals square root of 4 minus x squared. Now it's a semicircle. It's the top half, right? Because y equals a plus. So top half of the circle, back to negative 2, 0. Okay, so good. There we go. Now, the question. Find the counterclockwise circulation. So we're asked to find the integral along the curve f dot t ds. Now, if you're wondering, wait, what is f dot t ds? Well, this is the same thing as the integral along the curve of your m dx plus n dy. So it's just different notation. So in particular, this is the way that Green's theorem is set up, where, to be clear, this is your m, and this is your n. All right, so, like, cool. Well, we're going to use the power of the theorem. So we're going to think of, hey, you know, this curve is bounding a region. And the region is the top half of a circle. It's a half a circle. And so we'll mark it, and we're going to say, well, let's use Green's theorem. So it's sort of like, why do the problem that they asked us to do? Let's see if we can't find a simpler thing which would give us the same answer. Because that would make things simpler, right? And we like things being simpler. It's part of the goal in math, is to say, I want the answer, but I also don't want to make mistakes. So I want to make sure I do things in a way that's simpler. And it's all a matter of simplifying to get from point A to point B, so that we get all the points along the way. All right, well, let's begin. So we say, hey, we just pull out Green's theorem. And so we're going to put Green's theorem here, which unfortunately is marked in orange, but that's okay. And it's still true. It's not green because of the color. There's no purple theorem. And okay, so this is the integral over our region. And by the way, we do appreciate it being counterclockwise. That means we don't have to worry about sign changes. Integral over our region of n sub x minus m sub y. Okay. Well, let's see what that would be. So n sub x, that 8y cubed goes away. N sub x would be 6y. 6y minus m sub y. Well, what's going to happen here? That goes away. That goes away. 2y squared. That has a y in it. So that is a 4y. Okay. So this becomes an integral over our region of 2y. Now, nothing cancels, nothing simplifies. We're not going to just be able to do an argument area. So we say, okay, no worries. We can just do the integral. Now, let's think about how we're going to do this integral. We have a couple options. We could do it in Cartesian coordinates, but I'm biased. When I see circle, I think polar, because polar's pretty good at handling circles. So since I see a circle in the shape, even though I don't see an x squared plus y squared, let's go for polar. Okay, so we're setting up our integral. So as we set it up, we'll get our bounds in a second. We say, well, y in polar is r sine theta. So remember, in polar, x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. Those are our basic formulas for us to know. So y is r sine theta. dA adds another r, so r dr d theta. Now, where does theta go? It's not all the way around. It's halfway around. So we're starting here at 0, and we're going to end at pi. So 0 to pi. And now, what about r? Well, r says, how do you relate to the origin? So we start at the origin, and we go out until we hit the circle. So we start at distance 0, we stop at distance 2. And that's our integral we have to figure out. Now, the good news is, these are really, really nice bounds. Numbers to numbers. And the function we can separate as like the theta part and the r part, right? So we have these two parts. So what we can do is we can actually say, hey, this is like the integral from 0 to pi of sine theta and integral 0 to 2 of 2r squared dr. Okay, so for the integral from 0 to pi of sine? Well, the integral of sine is cosine, negative. Don't forget the negative. So negative cosine, evaluated 0 to pi. Plug in pi. Cosine of pi is negative 1, but you have that minus. So minus minus 1 really makes a plus 1. Then we're going to subtract. Plug in 0, you get cosine of 0 is 1, but there's a minus there. So it's 1 minus minus 1, so it's really 1 plus 1, which is 2. Okay, so we have a 2 times. Here, what do we get? Well, we get 2/3 r cubed. Right? Add 1, divide. And it's r squared because we have both an r from the y and an r in the dA. So don't forget that r in the dA. Evaluate 0 to 2. Plug in 0, you get 0. Plug in 2. 2 cubed is 8. 8 times 2/3 makes 16/3. 2 times 16/3 gives us 32/3. And there we go. Woohoo! Nice! All right. Whew. Good. Good. Let f be the vector valued function given here. And let c be the path along the x-axis. Okay, let's draw this. Starting at -2, going over to +2, and then back along the semicircle y equals square root of 4 minus x squared to -2, 0. Huh. I'm getting some real strong deja vu vibes, because this feels like the same curve and the same f that we just did. So what's different? Well, find the outward flux f dot n. Now, if you remember the last one, it was circulation f dot t. Now, that's the version of Green's theorem that we usually talk about. So this is a slightly different version of Green's theorem. So here, we're looking at how do things cross through the boundary. Well, can we still use Green's theorem? Yes, but we'll state it in a slightly different way. But same idea. We still have our same region. We still talk about the boundary of our region. We still talk about our orientation. So the good news is we are oriented in the right way, counterclockwise, or as I like to say, in case we ever encounter regions with holes, we orient so that our region is to the left, to the left. When you walk your curve, keep the region to your left. Okay, all right, good. Now, you're going to be like, Steve, you've ruined Beyonce forever. Ah. On the other hand, orientation is permanently fixed in your mind. So, what's the new way you do this? So here's the fun thing. When you're thinking about flux, and in fact, this will not be the last time we talk about flux, so it's good to remember this. When we're talking about flux, it's connected to divergence. So that's the thing to remember. Flux becomes divergence. All right, so that's what we're going to use. This is the version of Green's theorem appropriate for this setting. All right, now with that in mind, we say, okay, well, let's do this computation. So we need to compute the divergence. So how does the divergence work? Well, that's going to be the integral. You take the derivative of, if we still call these pieces m and n respectively, then it's going to be partial m, partial x plus partial n, partial y. The nice thing here is you don't have to stress about, wait, which one is added, which one is subtracted. That's all gone. And in some sense, you still have nice derivatives. It just depends on the function. Well, let's see what we have here. Well, we have the integral of 24x squared minus 6x plus 0 plus, here we're going to have 24y squared plus 6x, and okay, there we go, dA. Now, some good news for us. Things were planned so that at least a little bit of niceness happens. Maybe a lot of niceness happens. But notice the 6 x's cancel. Good, good. Now, anything else happen? Well, we're setting ourselves up to integrate, and we look at this and say, when we think about what's happening, pull out the common 24, we're really integrating over our region, x squared plus y squared. And we're like, whoa, wait a second, x squared plus y squared, circles in our region, polar, right? So we'll write these down again because, hey, it's nice to have these as reference, and the more often we write them, the more quickly we'll remember them. It's one of these things where if you write stuff, it forces you to remember stuff. Whereas if you watch stuff, yeah, maybe, but you'd have to watch it a lot. Especially if you watch it at like 1.5 speed, you probably have to watch it like 3 or 4 times. So write stuff down. It's amazing what it'll do for you. Now, for us, what do we have? This becomes 24. Integral, we'll worry about the balance in a second. X squared plus y squared becomes r squared. dA, r, and then dr d theta. Theta goes only halfway around, 0 to pi. R, always start at the center, work your way out. So we start at 0. When we go out till we hit the curve, which is the circle of radius 2. Now, this is going to be good news for us because we can split these integrals. 0 to pi d theta and 0 to 2 of r cubed. Well, this first integral, no big surprise. That's going to give you theta. It's theta evaluated from 0 to pi. The second integral will actually work through. Be a little bit careful here. 1/4, and then it's going to be r to the 4th, evaluate 0 to 2. Well, plug in 0, you get 0. Plug in 2. 2 to the 4th is 16. 16 divided by 4 is 4. So this is 24 times theta times 4, or 96 theta, because 24 times 4 is 96. And there we go. That's the flux. So in other words, if this would say, if you thought of this F as being modeling a flow, we have an outflow, actually quite a bit flowing out. So, okay, so there's a lot flowing out of this region. And that's it. That's all we have to say. We just need the number. It could be a positive number, could be a negative number, and we're fine with that. But of course, the big thing for this problem is just remember, when you're finding f dot n, use divergence. All right? You got it? You got it? I believe in you. Don't forget. You'll be fine. Come on, do it. You'll be great. Yes, 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 yes. Evaluate the integral on the curve f dot t ds, where f is our vector valued function, 2 log x squared plus y squared, 3 arctangent y over x, and c is the counterclockwise oriented boundary of the region defined by the polar inequalities 1 less than or equal to r less than or equal to 3, pi over 6 less than or equal to theta less than or equal to pi over 3. Okay. All right. Let's look at our region. Let's get a handle on that. And so if we're in the plane, we have pi over 6. That's like a 30-degree angle, so we'll say that's roughly pi over 6. And then pi over 3 is roughly a 60-degree angle, so let's say it's something like this. So this is theta equals pi over 3. And then r equals 1. Well, that's a circle of radius 1. And then r equals 3 is a circle of radius 3. So our region is this part right here. So here's our region. And we're told it's counterclockwise oriented. So here's C, and orient counterclockwise. Now, if you ever saw clockwise, we can do that too. Just keep in mind, if the orientation is going the wrong way, fix your sign. All right? Fix the sign. Okay, so good. Now, we might as well highlight that this does indeed, it's a closed curve. It does bound a region. So we'll fill it in. And it's a piece of a wedge, right? maybe like you can think of it as a part of a donut or something. All right, so here's the region R. All right, good, good, good. Now, what are we going to use? Well, this one doesn't explicitly tell us, but we're going to use Green's theorem. What's our clue? Well, we're seeing clues like closed curve. It really emphasizes our orientation, or in this case uses words orientated. Kind of a strange word, but that's all right. It's still a word. And but closed curve orientation matters. And f dot TDS, which is just another way of saying, by the way, m dx plus n dy. Know the different ways that we may write something down. Lots of different notations exist, and you have to be comfortable switching back and forth and finding the one that's right for you. Okay, so let's work this out. So according to Green's theorem, because I do not feel like integrating log of x squared plus y squared, does not really feel like that's my jam today, if I may use the term. Well, so what can we do? Well, we'll say that this is going to be the integral around the curve f dot t ds is equal to the integral over our region of n sub x minus m sub y. Okay, so we're in proper Green's theorem. Don't forget the dA term. So here we're going to have some fun derivatives to work through. Okay, so taking the derivative of n. So this part is your n, m comma n. So let's see, arctangent. Maybe I should take that down here. So we're going to have 3 times 1 over 1 plus y over x quantity squared. Okay, so the 3 is just the 3, comes along, arctangent, 1 over 1 plus the inside squared. Chain rule that, derivative of the inside. Now you have to remember, what derivative are we talking about? We're talking about the derivative with respect to x. So y is like a constant, so there's going to be a y. And then what's the derivative of 1 over x? Negative 1 over x squared. Okay. All right. So, cool. Well, you can do the following. Imagine, see this x squared? Imagine it's in the denominator, which is not too hard to imagine because it's in the denominator. And so multiply it through this denominator. And what do you have? Well, on the numerator, you get 3 times minus 1 times y. Minus 3y. Then downstairs, x squared times 1 makes x squared. And here, this is really y squared over x squared times x squared, which makes y squared. All right, so we have minus 3y over x squared plus y squared. Subtract, okay, m sub y. Now this one we can probably do in one step. So it's a log. 2, downstairs, you write the function, x squared plus y squared. Upstairs, the derivative of the function. Derivative of x squared plus y squared with respect to y is 2y. All right, dA. Good. Now, hey, we can combine. Minus 3y minus 4y. Okay, so this becomes the integral over our region of minus 7y over x squared plus y squared. Now, this initially does not look like the kind of integral we'd want to do. But what can we do? Well, the minus 7, okay, pull it out, no problem. But that's not the only thing we can do. We can go to polar. I mean, it kind of tells us we got polar. And the x squared plus y squared is confirming polarness. So we say, okay, well, let's just switch to polar. We can do that. All right, so we're going to have integral. What do we have? Well, let's remind ourselves, x is r cosine theta, y is r sine theta, x squared plus y squared equals r squared. So that's our basic rules here. So we have minus 7 r sine theta. That's our y. X squared plus y squared is r squared. dA is r dr d theta. And now we're integrating theta, well, goes from pi over 6 to pi over 3. Okay. Well, what about r? Well, r goes from 1 to 3. All right, well, that's good. Now, watch this. This is fun. What happens? Well, how many r's do we have? We have 2 r's upstairs, 2 r's downstairs. Boom, boom, boom. No more r's. Oh, the r's are gone. Ho, 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 ha, ha, ha. Okay, so we can do the following. We can pull out the minus 7 in front, and then we can say, look, this is really pi over 6 to pi over 3 of sine theta. And then we have integral 1 to 3 of dr, just pulling apart the integrals. And the integral from 1 to 3 of dr is 2. So really the hard part is this part. All right, well, let's work that out. So negative 7 times 2 is negative 14. The integral of sine, well, that's going to be negative cosine. And then we're going to evaluate from pi over 6 to pi over 3. And, well, negative, negative. Okay, we can get rid of that. And what do we have? Well, we have 14. Now, what is cosine of pi thirds? It's a half. And, all right, know your trig values, unit circle. 1/2 cosine pi over 6, root 3 over 2. All right, and okay, now you can multiply through. 14 times a half, that makes 7. And then 14 times root 3 over 2 makes 7 root 3. And there we go. Now, this is actually a negative number because root 3 is slightly bigger than 1, and that's okay. It's okay to get a negative number because that just means that it's sort of, if we call this circulation, we're sort of spinning in the wrong direction. It's trying to spin us in the other way. And but there we go, right? That's our process. We set it up, take our derivatives, being very careful, and other than that, yeah, it's feeling very, very familiar. And at this point, we're like, man, we are ready. Like Green's theorem, that's our jam. And which is good because I'll tell you, between me and you, because nobody else is here, right? It's just us. They love Green's theorem problems. So you kind of know there's a Green's theorem problem in your future. So, all right, just had to say that. Okay, well, good. Let's keep going. Find the surface area of the portion of the surface z equals x squared plus y squared lying between the planes z equals 1 and z equals 9. All right, so let's talk about our surface. Z equals x squared plus y squared, classic shape, also known as the bowl. It's a elliptic paraboloid if you want to sound very fancy, but of course we're very informal here, so we're going to call it the bowl. So we have a bowl here. All right, so here's our bowl. Now what's happening? Well, we're going to slice the bowl and say, look, we're not trying to find the surface of the whole bowl. We're going to take a slice down below at z equals 1. So we got the bottom. And then we're going to take another slice at z equals 9. And that's the top. And so, my picture is getting somewhat convoluted here, but we're just finding the area in between there. So that little stretch. So if we're being careful, and we can even mark this back here, right? Yes? Well, okay, maybe my picture got too messy, so let's just draw it one more time. So we have this small part down below, and then we're going up, and then we have this larger part up above. And so this is at z equals 1. Here we're at z equals 9. And yeah, there we go, right? So there's our picture. All right, so what are we going to do? Well, the good news is we have a formula for it. Aha. So since we have a formula for it, what should we do? Let's use our formula. Yes, exactly. We're going to use our formula to find our surface area. Okay, so now the thing is, surface area, there's only a very small number of surfaces that work. And the good news is we saw one, planes. This is another one, bowls. By the way, if it was x squared minus y squared, everything we're about to do carries over. So that's saddles. So we can do bowls, saddles, planes, spheres, cones. And did I mention planes and bowls and saddles? Pretty much that's it. It's not a very long list. And so be prepared to be like, haven't we seen this one before? Yeah, because there's like four or five that we always pick from. So, all right, so let's go ahead, write down the formula. We have that our surface area, if we think of this as our surface G, it's the integral on our surface of dSA, but it's also equal to the integral over our region of the square root 1 plus fx squared plus fy squared dA. Now, to use this, we need to understand what exactly is meant here when we are saying our region. What is this region? Okay, so here's the idea. We're going to take this and we're going to try to visualize. This is one of the things that makes this class challenging for some people. And so imagine we have our z-axis. Now we're going to pick it up and we're going to look straight down the z-axis so that the z-axis is just a single point. Okay, so like take this shape here and we're going to pick it up and look straight down. And when you turn it and look straight down, the top looks like a circle, and then you have the sides, and then you have the bottom looks like a circle. And so what's happening is from above, this is what you're seeing. You're seeing the inside of that surface from above. And so you're saying, okay, now what is R? Well, R is the shape that you see. So if you were to imagine projecting this down, and that's a really terrible picture I just drew. Okay, so imagine I can do a better job of drawing a picture. So you're going to see a pair of circles. There we go, pair of circles. There we go, yes. Ha ha ha. That circle, I've never seen that circle before. All right, so, okay. So this is our region R. All right, so here's our region R. What we see if we were to look directly at our surface from above, down the z-axis, what do you see in the xy plane? All right, now with that out of the way, let's start our computation. So we have the following. This is equal to the integral over our region of the square root of 1 plus f is the surface. So this is your f of xy. F sub x, derivative of x squared, 2x. F sub y, derivative of y squared, 2y. And dA. All right, well that's the integral over the region of the square root 1 plus 4x squared plus 4y squared, or 1 plus 4 times x squared plus y squared. And now we're like, well, how are we going to integrate this? Yeah, no surprises. We're going to go and do polar. We see x squared plus y squares. We see circles polar. Polar, polar, polar. All right, so here we go. Integral, square root of 1 plus 4. By the way, square root we can write as 1 plus 4. This becomes r squared to the 1/2. dA, r dr d theta. Where does theta go from? 0 to 2 pi. And where does r go from? Now, think about the picture. From the center, we haven't hit anything until we hit 1. And then we're in our region till we hit 3. So we're going from 1 to 3. And you might say, wait, how did you get 3? Because it's the circle x squared plus y squared equals 9. So it's equals 9. How did I get 1? X squared plus y squared equals 1. So I'm just replacing z, where the value is 1 and 9, to see what the circles are. Should have said that earlier. That was my bad. I'm sorry about that. Okay, well now, yeah, this isn't too bad. Well, at least we've seen worse. So what can we do? Well, we can certainly pull apart and say this is 0 to 2 pi d theta. And that's one's a freebie. And then 1 to 3, 1 plus 4r squared to the 1/2, r dr. And okay, so that's 2 pi, like I said, freebie. Here, well, substitution. U equals 1 plus 4r squared. What would du become? 8r dr. Or I can make this 1/8 du is r dr. So we have our 2 pi, don't forget that, our 1/8, which is going to come from the r dr integral, u to the 1/2 du. The last thing is the bounds. Plug in. R equals 1. 1 plus 4 makes 5. R equals 3. 3 squared is 9 times 4 is 36 plus 1, 37. Oh my goodness. What a number. That's all right. It's a number. We aren't too scared by that. All right, so 2 pi times 1/8, that's pi over 4. Okay, so that's the part in front. Then we're going to have u to the power 3 over 2 times the reciprocal 2 over 3. And evaluate that from 5 to 37. Now, these are not nice numbers. 5 to 3/2, 37 to 3/2. That's okay. We'll just leave them as what they are. We can do a little bit of simplifying in the front. So this becomes pi over 6 times 37 to the 3/2 power minus 5 to the 3/2 power. And there we go. That's the area. All right. Is it the prettiest area? No. Did we find it? Yes. Should we be happy about that? Absolutely. You know, we should celebrate our successes. And this was a success. It wasn't the easiest thing to find, and so life is good. All right, so make sure you know this area formula, the square root of 1 plus fx squared plus fy squared. It does show up in surface area, but it also shows up in some applications. You know, things like finding mass and center of mass and those types of things. So be ready. Be prepared. Know how to use it. All right, good. Good. Let G be the surface of the cone. Z equals square root 3 times x squared plus y squared, where Z goes from 0 to 6. Evaluate the surface integral. Integral on the surface G, y squared dsa. All right. Well, let's talk about what's going on. So we have our cone, and it's Z equals square root 3 x squared plus y squared. Okay, it's going up a little bit steeper than the typical Z equals square root of x squared plus y squared, not too much. And up here we have Z equals 6. And so it's not a solid, right? It's just the cone itself. So, okay, so now what do we have? Well, we're trying to integrate on this cone y squared dsa. And so, okay, great. So it's a surface integral. Now, what do we do? Well, we think about what's going on pictorially. All right. So our goal is we're going to push this into an integral in the xy plane. So we have to think about how we're going to achieve that. So imagine, if you will, that you were looking here and you have your eye looking down and you're looking straight down the axis. And okay, so you can tell here I don't draw Okay, imagine I'm not trying to draw a knot. But imagine you were trying to look straight down. I should get better at drawing. I'll practice that. What will you see? Well, what you'll see is this right here, that's sort of the outer edge of that surface, is going to become a circle. And so your region down in the plane is a circle. Now, the question, and this is an important question, is which circle is it? All right, well, to answer that, what we're going to do is think about how we have z. We have z equals 6, so we're going to say, okay, so that's 6 equals square root of 3 times x squared plus y squared. Or you can square both sides. 36 equals 3x squared plus y squared, or 12 equals x squared plus y squared. So this is going to be a circle of root 12, right? That's your r squared. Circle of radius square root of 12. All right, well, that's fine. That's no worries. It is what it is. Okay, so now what are we going to do? We know our region. You say, okay, great. So we're going to convert everything into our x's and y's. Y squared we can do automatically. And x's and y's automatic. What if there had been a z involved? No problem. If there had been a z, we'd throw this in. So we want everything in terms of x and y. That's already there. Life is good. What about this part, DSA? Not automatic. We're going to have to work through that. So let's go ahead and take a few minutes. And this will be the part that is probably the most computationally intensive. And that's okay. That's all right. We can handle a little bit of computation in our lives. All right. So I'll go ahead and write this out. This is 1 plus fx quantity squared, fy quantity squared, and then dA. So once we have our handle on that, then the real work will begin. All right. And as a reminder, this is our f of xy. Okay, so let's come down here and do some work. So 1 plus fx squared plus fy squared, that's 1 plus. Now, if we think of this, I can think of this as square root of 3. I'll just think of that as separately. This is really square root of 3 times x squared plus y squared to the 1/2 power, right? It is. So square root of 3, 1/2 x squared plus y squared to the minus 1/2 times 2x. And that's going to be squared plus, same thing, square root of 3 times 1/2 x squared plus y squared to the minus 1/2 times 2y, quantity squared. Okay, so there's our fx squared, fy squared. Now, the 2 and the half cancel. 2 and the half cancel. And so what do we have here? We have 1 plus, this becomes 3x squared, because 3x squared, remember we're squaring, over x squared plus y squared, because that's going to go downstairs, negative exponent, square of the square root goes away, plus here 3y squared, okay, downstairs x squared plus y squared. Now, if you add these last two together, you're getting x squared plus y squared over x squared plus y squared, also known as 1. So this is why cones, it's possible to do surface area, because you get some nice simplification. It turns out that this part right here will become a number. What number? Well, in our case, this part on the inside became a 4. And the square root of 4 is 2. So 2y squared. All right. Good. Good. All right. We're making great progress. And now we say, okay, so we don't have to think about a surface integral. It's an integral over a region in the xy plane. There's no z part anymore. So surface integrals, it's all about pushing it down into the plane. So that's what we've done. Well, how are we going to carry out this integral? Let's go polar. It seems like a theme. They really love polar coordinates on this one. I don't know what it is. That's all right. Just means we're going to get really good at doing polar. Okay, integral of 2 r sine theta squared. And then we're going to have our r dr d theta. And where does theta go? All the way around. 0 to 2 pi. Where does r go? Well, from the center out to the circle. And so from 0, the origin, out to square root of 12. And square root of 12 is another way to say 2 square root of 3. All right. Okay, good. Now, what comes next? Well, we can sort of whoosh things, push them around. The 2 is a constant. That can go all the way out. So this is 2. Integral, let's pull out the theta part, sine squared. Now that's going to take us a minute, but that's okay. I mean, we get like 10 minutes to do these problems, so a minute, that's not so bad. What do we have? R squared r. So that's r to the third, r cubed. And, whoops, I forgot my integral, 0 to 2 root 3. Okay, let's try that again. Integral 0 to 2 root 3 of r cubed dr. Okay? Good. Okay, so we have our 2. Now, let's talk about sine squared. Do you remember how to do sine squared? Yes? We dig into our trig identities. So sine squared is 1 plus cosine 2 theta over 2. No. 1 minus cosine squared. That's 1 plus. Okay, yeah. Those are our power reduction identities. Good ones to know. Okay, so we have ways to handle this. So sine squared, this really becomes 1/2 minus 1/2 cosine 2 theta. Okay, well, that we can integrate. Okay, so that's 1/2 theta. Integral cosine is sine. Have to, accommodate for that 2. So that divide by 2, 1/4 sine 2 theta. And then you have to plug in from 0 to 2 pi. When you plug in 2 pi, 1/2 times 2 pi is 1. Okay, 1 pi. Sine of 4 pi, 0, 0, 0. Sine of 0, 0. Okay, so we get 0. Okay, good. Okay, except for that first term pi. All right, so this integral pi. What about this integral? Well, we have to do this one. Okay, so we integrate integral of r cubed, 1/4 r to the 4th. And then we're going to evaluate from 0 to 2 root 3. Well, now I feel like I want to put root 12 back in. So this is 1/4 times root 12 to the 4th. I might say, that sounds complicated. But build up to it. Think of it, if I take something to the 4th power, it's like a square and a square. So this is like 1/4 of 12 squared. And like, well, that's easier. In fact, I can think of it as 1/4 times 12 times 12. And 1/4 times 12 is 3 times 12, which is 36. So we have 36 pi and 2. Put them all together, and we're left with 72 pi. There we go. That's our answer. Wow, I'm actually kind of amazed. I was really expecting there to be at least one root 3 showing up in the final answer. So cool. That was actually really nice. Wow. Wow. Isn't it fun when math works? Oh my gosh. Oh, good times. Good times were had by all. All right. Good. Good. Let's keep going. Let's keep having some more fun. Find the flux of the vector field f of xyz is x squared xy 4z in the positive z direction, which means upward, pointing normals upward n, through the part of the surface z equals 9 minus x squared minus y squared that lies above the xy plane. Okay, there's a lot of words here. Let's make sure we understand what's going on. So there's a surface here. So let's start with that part. So we'll start with things that we're comfortable with, and we'll build up to what's going on. Now, when we look at this surface, we recognize it. We say, oh, if it was like z equals x squared plus y squared, that's a bowl minus the bowl turns upside down, things spill out. 9 shifts up. So 9 minus x squared minus y squared is this bowl here. All right, now, do we want the whole thing? No, no, no. Just the part that lies above the plane. So I say, oh, okay, cool, 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 cool. So it's like we come up here to 9, and then we have this bowl that just drops down until we hit the xy plane. It's not a solid, it's just the bowl, right? All right, good. It's empty. Of course it is. You turn it upside down. Nothing's going to stay in there. All right, so here's our surface. So here's our surface. Now, what do we have? Well, with surfaces comes orientations. So that's what this n is talking about. So this n is an orientation. And so in particular, we can think of it as at every point we have a direction. Now you have to pick a side, right? So that's why it says upwards n. So here, you know, if you go through, it varies depending on where you're at, but the ends are like if you were standing on the surface, imagine you were a very tiny person, you know, where's your head poking out? That's the orientation. So we have this orientation going with the surface. Now, independently of this, this is not the vector flow. There's a vector flow going on. And you're trying to find the flow through the surface. Now, how do you find flow through surface? So flux means flow. And I know you're thinking like, what, the flux? No, no, it's what the flow, right? So flux is, if you want to find that, you're integrating over your surface, I'll use G for surface, of F dot N. So this is flux. All right, so that's what we're trying to compute. So we have this surface that's oriented. So when we talk about the flow, we say, well, is it going, you know, in the positive or negative? Like, okay, which way do things flow? So we want to have a sign. That's an orientation. When you want to pay attention to direction, that means orientation is involved. All right. Now, what's the formula? Okay, so here's the formula to remember. And it's a good formula to remember because it makes these problems come from like, this seems impossible. Like, well, that seems perfectly fine. All right, so if you have an upward normal and to the surface z equals f of xy over region R, okay, so this is your assumptions, and then the integral of your m and p, so this is your flow, your vector function, dot n, so sorry, this is your computing the flow, but this is your vector field. It's equal to the integral over your region R of minus m fx minus n fy plus p. Okay, that's it. No square roots, nothing vectors left. It's all pushed down into the plane. And then one small caveat, and the caveat is any z term in m and p is replaced by your f of xy. That's it. That's the whole thing in a nutshell. Now, why does this work? Well, we already have our M and P, and this it feels like a dot product, and it basically is a dot product. Because what's going on is this NDSA is minus Fx minus Fy1 dA. That's what it boils down to. And if you think, well, where does this minus Fx minus Fy1 come from? This part right here comes from the gradient of z minus f. And so if you compute the gradient of z minus f, this is what you get. All right, so that's the formula. Now, you're like, okay, he's spent a lot of time writing the formula. Is he going to have enough space to do the problem? I don't even know. Let's find out, because I suspect most of these, they're just going to say it's a test of the formula, so the actual integrals involved are going to be more straightforward. Of course, that's the hope. We're going to hope really hard. And all right, let's find out. Let's see what we get. So according to the formula, this will be the integral over our region. And we still have to talk about our region. We'll get to that in a moment. But let's go ahead and run this computation. So it's minus m x squared fx. So this is your f of xy. So f sub x is minus 2x. And then it's your minus n, right? So there's no derivatives. It's just literally m and p. So minus xy times f sub y, minus 2y, plus p, plus 4, and I'll write z here for right now, but then we say, wait, we can't have a z because we're going to be in the plane, so we're going to replace our z here by 9 minus x squared minus y squared. Okay, so minus m fx minus n fy plus p. All right, okay. I'm sorry. I feel like I'm being overly dramatic here. And I'm like, oh, what's going on? Oh. All right. Okay, so this becomes integral over our region of x cubed plus 2x cubed, 2x cubed plus 2xy squared plus 4 times 9 minus x squared minus y squared dA. All right, now it's time to talk about our region. So how do we find our region? Well, imagine that we're way up here and we're looking down the z-axis. And like, what do you see? Whatever you see, it's like you're squashing your surface, just like push it flat into the xy plane. What do you see? Well, we're really going to see the outer edge is this piece right here, which is caused when we have the xy plane itself at z equals 0. So it's like, oh, so what we're seeing is a circle. And what circle is it? Well, the outer part is where 9 minus x squared minus y squared equals 0. Or x squared plus y squared equals 9. All right, now, some good news. We have 3 terms. 2 of them we can do with no work. They're free. Do you see which 2? And why? Okay, so let's talk about what's going on. So let's look at this first term. Now, initially, it looks like we're going to have to do work. And that goes against our belief system. Like, wait, we didn't become mathematicians to do work. We became mathematicians to solve problems where we make things simpler without work. So what can we do? Well, notice x cubed. So if I am, say, something over here, I can pair it with something over there. So in other words, this region has symmetry. Now, the contribution from this part versus the contribution from that part, how do they relate? Same value, different sign. So what's going to happen? So this is going to be 0. And it's essentially, you have an odd function, so you have symmetry. How about this? Same argument, right? The contribution from this part versus the contribution from that part, same value, different sign. Again, you'll get 0. And because the x part is odd, and you have symmetry. So by symmetry, you can say, okay, those parts, poof, go away. Now, if you like to do a lot of work, feel free to do it. But I personally feel, let's not. All right. So now we have this last part. So, okay, 4, 9 minus x squared minus y squared. This feels very much like something we should do in polar. So we're going to do it in polar. Okay, so this will become integral. So this will become 4 times 9 minus r squared. That's this part. dA, r, dr, d theta. Where does theta go? Full circle, which is good because we used that symmetry. So it's good we went all the way around. Where does r go? From the center all the way out to the edge. 0 out to 3. Now, you can pull off the d theta integral to the front, and since I'm a little bit short on space, I'll squeeze it in and say, okay, look, the d theta integral gives you 2 pi. Great, cool. Now, this part right here, before we integrate, we would distribute through. So let's go ahead and distribute everythh through. So we have that, and we'll bring in the 4s as well. So that would give you 4 times 9 times r is 36r, 4r squared r, 4r cubed. Okay, when we integrate that with respect to r, what do we get? Well, we'll get r squared over 2 times 36, 18r squared. Minus r cubed becomes r to the 4th over 4, but times by 4, minus r to the 4th. And we're going to evaluate that from 0 to 3. Now, you can pull out an r squared, so this is r squared 18 minus r squared. When you plug in 0, you get 0. When you plug in 3, you're going to get 9 times 18 minus 9, which is 9. Now, if you like, you can really think this is 18 times 9, which is 162. 3 to the 4th is 81. And then if you take 162, subtract 81, you do get 81, which is 9 times 9. All right, so 9 times 9 times 2 pi. Final answer, 162 pi. Nice. Whew. Good. Well, of course, we saved ourselves by symmetry. But really, the big thing about this problem was making sure we know how to compute flows through surfaces. So MNP.N, we have a formula for that. And then we're good to go. Nice. Good. Let G be the part of the surface Z equals sine 2x to the 5th minus 3y to the 4th. What? That's crazy! Yes. Now, normally when you see something crazy, that's like a sign, like something's nice gonna happen. Okay. Line above the region R, described by x greater than or equal to 0, y greater than or equal to 0, x squared plus y squared is in between 1 and 4. Now we can quickly sketch that. And so x greater than or equal to 0, y greater than or equal to 0 means we're in the first quadrant. X squared plus y squared equals 1 is a circle of radius 1. X squared plus y squared equals 4 is a circle of radius 2. So there's circle radius 2. And so our region R is in between. Okay, so here's our region R. Now, you might say, hey, what does the surface sine 2x to the 5th minus 3y to the 4th look like? Hopeless without technology. But that's okay. We're not asked to plot it. And if you do, it's kind of a pretty picture. You don't look too far away because there's so many wiggles, it becomes almost incomprehensible. but in the small, yeah, it's kind of a fun picture to draw. All right, now, here we go. So we want to find the flux for F, and it's really going through that surface, and, right, there's an extra period. Okay, through the surface where N is the upward pointing normal. All right, so you might say, wait, N, how does N fit into this? Well, N is an orientation for G. So that's where N fits into this. Okay, so we're asked to find the integral of our surface G of F dot N dSA. Now, if you remember, what is this? This is the integral over the region. Right, so here's our region. And now normally DSA has a messy part, but N has a similar messy part, and their messiness cancels each other out. So which is really good. So this is going to become R minus M Fx minus N Fy plus P. So this is the default formula. Just make sure you're in the right orientation. Now, if your orientation is ever the wrong way, easy to fix. Minus, because a minus is an orientation. All right, and then this is our f of xy. Now, the good thing is we already have our f of xy. There's no z's, no z's at all. So it's just a matter of cleaning this up. Okay, so let's see what we have. We have our integral over our region of minus m, so that's 6y cubed, f sub x. Okay, so derivative of sine, cosine, inside stays the same, times the derivative of the inside with respect to x, which would be 10x to the fourth. Okay, so this is our mfx minus n, 5x to the fourth, times our fy. Okay, so there we go, fy. Derivative of sine is cosine. Inside stays the same, deja vu, times the derivative of the inside with respect to y, 12y cubed. Okay? And then plus p, plus, and 2xy over x squared plus y squared. All of that dA. Now, fingers crossed, if we've lived a really good, clean calculus life, and our teachers like us, and let's hope that both things are true. And I think both things are true. I think we've lived a good, clean calculus life, and I do think our teachers like us. We seem like nice people. They seem like nice people. Let's all get along. What should happen? The crazy parts should disappear. Well, they both have cosine. Let's look at what's attached. Minus 60 x to the fourth y cubed. All right. Cool, cool, cool. Oh, and I just noticed I forgot something. It was like, it's not canceling. What did I forget? Derivative of minus 3y to the fourth is minus 12y cubed. Okay. Yes, pay attention to small things. All right. I was worried. I wasn't canceling, but now, okay. Minus 60x to the fourth y cubed plus, because two minuses, 60x to the fourth y cubed. No, they cancel each other out. Okay, so these terms cancel. Yes, we are canceling. That's not to say we're part of cancel culture, but we like it when things do cancel because, that makes life simpler. We like that. We like that. All right, so here we go. We're down to the following. We have the integral over our region of 2xy divided by x squared plus y squared dA. Now, how are we going to do this one? Well, it's feeling polar, right? Yeah, the region. Come on, give me a break. Of course it's going to be polar. Okay, so this is the integral over what? I should give myself more space. Integral. So, as a reminder, we have x equals r cosine, y equals r sine, and x squared plus y squared equals r squared. All right, so those are our basic formulas. So we have 2 r cosine theta, r sine theta, over r squared, and then dA is r dr d theta. Theta is only in the first quadrant, so that's from 0 to pi over 2, right? So 0, pi over 2. R, how do we go out from the center? We start at 1, we go to 2. So r 1 to 2. Well, cancel again. Nice. How about this? 2 times cosine times sine. What is that? That's going to become sine 2 theta. Oh my goodness. It's like they want us to get a nice answer. They're so nice. They're so nice. We should send them a thank you note when this semester is over. All right. So we get integral 0 to pi over 2 sine of 2 theta. And there's a d theta there. And okay, that's the theta part. And integral 1 to 2, the r part. Well, okay, integral of sine, negative cosine. Don't forget to, you have to account for that too. So negative 1/2 cosine 2 theta. Evaluate from 0 to pi over 2. All right, we'll work on that. And the other hand, here we have 1/2 r squared. Evaluate 1 to 2. Well, okay, plug in pi over 2. 2 times pi over 2 is pi. Cosine pi is negative 1 times negative 1/2, makes 1/2. Subtract, plug in 0, cosine 0 is 1 times negative 1/2, so let's subtract negative 1/2. Well, 2 negatives make a positive. It's like orientation, right? If you're oriented this way, then a negative flips you, then another negative flips you back. 2 negatives, you're back to where you started. Your orientation flipped twice. And, okay, how about this? All right, 1/2. 2 squared is 4. 1 squared, 1. So 1/2 plus 1/2, 1. 1/2 times 3, 3 halves. And we made it. That's it. That's it. We did it. We got to the end. Huzzah! Oh, good times. Good times. All right. Well, this is our last problem on our last practice quiz. Oh my goodness, what a journey. What a journey it's been. Thanks for hanging in there. Thanks for coming all these times over and over and over. And I appreciate the trust that you've put in me. I hope I haven't let you down. I hope these have been helpful and that you've learned along the ways. And I feel like I should give out some, parting wisdom. And I can't think of anything better than to quote Albert Einstein. All right. Take care.